Good morning, everyone, and welcome back to those who joined us yesterday, and a warm welcome to those who are joining us today for day 2 of our hybrid summer school on medical informatics with artificial intelligence. First, I would like to thank everyone involved in making this event possible, as well as you that are here on site or online joining us. We received a number of questions regarding the activities in classroom, and just a quick reminder that from 12 p.m. to 1 p.m., we'll be answering all your questions through the WhatsApp groups or with our volunteers here on site. Yesterday, we began an exciting journey exploring how artificial intelligence is transforming healthcare. Back with us today is Professor Dr. Thomas Deserno, whose expertise in medical imaging and AI has shaped how technology supports clinical diagnosis. This time, he'll dive deeper into one of his areas of greatest impact, AI for medical image analysis, an area in where his research continues to shape the future of diagnostics and patient care. Please welcome Professor Dr. Thomas Deserno.
Thank you. Yeah, thank you very much for this kind introduction, and welcome back again here in Mexico City. It's a pleasure for me to give you a second lecture. We will, in order to understand how machine learning and artificial intelligence can be applied in medical image processing, I think it's necessary to understand at least roughly what medical image processing is about and how it is done without these tools, in order to understand how these tools can help. So I will give a short introduction. We will learn about the steps of medical image analysis, and two of these steps, for instance, image enhancement and feature extraction, are important. So we will have a brief look at what tools are used here, and then we will understand how machine learning approaches can be meaningfully integrated in these pipelines for processing, and also we will understand the role of those. But let us start with a motivation. That is a picture, an image. And my question to the audience, what do you see in that image? Sorry. No idea? I will show you what you can see here. Well, this is clearly a face. We have the two eyes, nose, mouth. Okay, I see you all recognize the face now. This is a set of pixels, black and white pixels. Regarding from the face or the shape of the face, you might suggest this is Jesus. Now, who of you is able to write a short Python script, analyzing this image, getting the output Jesus? And none of you can do that. I still can't do that neither. And that is the reason why we have this image processing still as an ongoing problem. What is an image at all? I like to define an image regarding its structures. So what we see here is a panoramic X-ray from the jaw, but that is not the point I'm showing the image. I'm showing the image because we can define the image based on the pixels, so the raw data, describing the entire image. And keep in mind, the saying, an image says more than 1,000 words. Try to describe this, what you see here in this image, with as much words as you can, and still reading that by others, they will imagine a different picture. So we also have particular points, which are addressed in this picture, maybe due to high contrast. We can define lines. And we can define areas. And the interesting thing is that there are some areas in this picture, unfortunately the resolution is not that good, but you can recognize a trabecular bone structure, which I marked here a little bit, but it's hard to say where it begins and where it ends in the image. So we have in a two-dimensional image, we have something like a region without the border, and we have maybe a tooth, yeah, which is a region clearly defined with a border. And that we can put in a so-called pyramid. Yeah? So we have the iconic description here from the radar, raw data, and the symbolic description here. Yeah? And these are the steps of processing, and all image processing, not only the medical image processing, aims to reduce information such that the information which is important for the task is still maintained, but the other things are removed from the image. So we have an information extraction here in that direction. Yeah? And regarding the panoramic X-ray, we could say local intensities regard to the pixel level. Local contrast may define edges. We have the spongiosa. We have some regions here, and then we have the switch between regions and objects. And that is what we have defined yesterday as the classification task. If you recognize that area is a molar tooth 2 or something, that is a classification task. And so we have objects like teeth and implants, and we have on the highest level something like the constellation of objects. And we are processing images in our brain on that level here. And what we need to teach the computer is to go in that direction. So this is just one example. We have the panoramic X-ray here that is done with dentists, and what they want to have is something like this, the dental chart, which tells you about all the teeth and how they are prepared and so on. And it is clear that this one here has more ledge information than this one. A lot of X-rays may result in the same dental status, but the important information is maintained, and how this information is extracted from the image, that is what image processing is doing. So the chain of image processing can be defined here with a formation. Then we have enhancement. These are algorithms basically operating on the low level, which is the pixel, edges, and maybe texture. And these areas here are usually on the high level. What does that mean? Well, suppose we have an algorithm. I take the photograph of the classroom here. The algorithm finds the faces of the people and then count the faces of the people. That algorithm might work here, but might not work for a related problem, maybe counting some fruits on the table or so. The reason is that we do assumptions into the algorithms on the higher levels, which make the algorithm working. And I will not go in details here, but this is the important thing for us. The analysis, where we extract features from the image that we might use for segmentation. Usually after the segmentation, there's another feature extraction step in order to compose that classifier we talked about yesterday. And then we have the classification in order to do some measurements from the identified region in the image. So medical image processing is defined as computer-assisted acquisition and analysis of medical imaging data. That is a textbook from a German colleague of mine, Heinz Handels. My previous name was Lehmann, so this is the definition I gave for medical image processing in our textbook on where it's more detailed. We have image processing for the healthcare enterprises in general, and defining these different steps. Formation, enhancement, and analysis is what we will talk about today. And analysis is composed of feature extraction, segmentation, and classification. Artificial intelligence, from our definition yesterday, are computer systems capable of performing complex tasks that historically only humans could do, and decision-making or problem-solving were some of these examples. So we now go in that direction here. But what is the difference between medical image processing and image processing? Why do we have this discipline? The one thing is that medical images are have a high variety. Here, for instance, we have some pictures. All these pictures are showing somehow the spine. In that picture here is an X-ray, we can see it. This is an MRI, we can see the individual spines. Here is a cross-section through spine. Here is the spine not seen at all because it's covered with some contrast agent. And suppose now you have an algorithm that is able to count the spines in that image. It will not work in that image. Okay, but even though we can say, well, yes, but I can design my algorithm for a certain modality and a certain positioning. These are all clinical images from the hand, which are used in order to guess the actual age of the person. But anyway, they look completely different. And not only with respect to the different individuals, if you look to the pictures of the same individual, they are differing. Here already I say intervariability, which means the same individual. But if you look to these two images, you might conclude it's from the same patient without knowing that here. And what you're doing is, well, you recognize somehow there are two implants. This is a tooth with a filling. You know that, of course, the shape of the filling may be changing depending on the projection. It's a 3D filling which is projected on a 2D object. And then you may see, well, having these two implants in the same orientation next to the same tooth, this is the same patient. And that is analyzing the image on the scene level. You identify objects, you identify the constellation of these objects, and from that you conclude. And if you would feed in these two images into a comparison, and you compare that pixel with that pixel and so on and so forth, none of these pixels will match. So that is the difference between the levels of processing. The next problem we have in medical image processing is that we usually do not have any ground truth. What we see here, a piece of bone, we see this structure of the bone, the internal structure, which is quite irregular. So we don't need any radiological education in order to understand that this certainly is sort of illness. Indeed, it's a bone tumor, which is shown here. But the question is, where does the tumor starts and where does the tumor ends? So we asked the medical expert to label that image. And the result is that one here. So the red shows clearly infected bone. The green one are healthy bone structures. Yellow is the background and so on. But what about this white region here? Well, that is a region the radiologists say, I'm not sure, I don't know. Okay. Now, suggest these two lines here are resulting from two of the programs you wrote for segmenting the bone tumor. Which one is better? If it... You want to answer? No, you can't answer. But how to decide then which algorithm outperforms another algorithm if it comes to some surgery, if it comes to some really critical decisions? And that is what I have here on the last example, the relevance. So if your algorithm does some mistakes in a setting like this, where the physician doing the surgery is really reliable on the computer pictures, then mistake in the calculation may yield to a loss of life. And that is the reason why we have this discipline called medical image analysis or processing. And as I mentioned before, the steps are formation, enhancement, feature extraction, and then classification, what we discussed yesterday. And I will a little bit explain these steps here. So we just have seen that orthopantomogram, the panoramic X-ray, which is a picture defined by 2 dimensions in the spatial domain, and just the grayscale, which is addressed to each of the pixels. We have other types of images in medicine, for instance, this ultrasound with the Doppler visualization. Actually, the ultrasound is a grayscale image and the Doppler is a grayscale image, but you cannot visualize 2 grayscale images into one. That is the reason why the second grayscale image is transferred into pseudocoloring and then overlaid. The red indicates blood flow towards the transducer, green indicates blood flow from the transducer, and with the labels here, aorta, left ventricle, right ventricle, we know that this is an image of the heart. This is one example for computed tomography, which ends up with 3 spatial dimensions and a grayscale associated to each of these pixels, but in 3D we do not call them picture element, we call them volume elements, so voxels. And the last example here is a video where we have 3 dimensions composed of 2 spatial dimensions and the time, which can be considered as a 3rd dimension. And we have here a real RGB image. That means each pixel in the movie is having 3 values for red, green, and blue. So the definition range may be from 1D to even 4D, if we have a sequence of volumes. The value range is the number of bands, could be 1, 3, or even more, depending on the imaging modality we are using. And so we can define the image simply as a mapping from the value definition range to the value range. And I will use X and Y coordinates if we are talking about a continuous image, but usually we have a discrete representation where for instance, the coordinates m and n runs from 0 to m-1 and so on. And we have the grayscales, which also are discrete defined. So now we come to image enhancement. And we can define different types of enhancement. We will what we can do in an image, we go through all the pixels, calculate based on the value of the pixel a new value. That is what we see here. The next step is region-to-point mapping. That means we still move over the entire image, but not consider only just one pixel, but the neighborhood of pixels in order to calculate the new point. And finally, of course, we could use the entire image in order to calculate one new point. And here are some, or I will, in the next section, give some examples for these algorithms. So feature extraction, what is that doing? Well, what is a feature? Usually we have this texture. I already mentioned that term as a region without a defined border. So that describes the internal structure. So for instance, if we have a 2D image, then we have a 2D internal structure describing that particular part of the image. And these are nice pictures published in 1966 for a different purpose, but they become popular in image analysis. These are photographs just from patterns. And we are clearly able to distinguish these patterns. Maybe due to the coarseness, these may be stones which are larger than the beans here. That may be some closed tissue or so on. But we understand differences between the internal structure of the objects. And then, of course, we can define characteristics on the shape. The shape could be defined as an ND structure in ND data describing the border of the segment. So that is describing the border, and that is describing the internal properties. And some examples here are maybe these lines. Very nice project at that time. The pathologist has a collection of these skulls. That was amazing. If I was in Aachen in his lab, a huge shelter just filled with skulls. And he was supposing that female, the orbit is maybe more round than with male skulls. Using these curves, we try to analyze this. But it is a different story. This is just an example for the shape of an object, in this term here, the orbit. So, classification, I will not go in details. We talked about this yesterday. All the tools we have for classifying. And then we are looking for tools that we can use for image enhancement. So this was what we have defined here. And I will give some examples for the histogram transform, which is a point-to-point mapping. We will talk about convolution, and one maybe special example of that convolution, which is the Sobel operator, and then the Fourier transform. So what is a histogram transform? Well, we have the grayscale, and we have the new grayscale, and we can define any curve that maps the old one to the new one. Very easy process, and that was used in the beginning of image processing on the computers. You cannot imagine the performance they have at that time, but the graphic cards was able to do these mappings, and that is the reason why they become such popular. Internally, you can calculate the lookup table, and then you simply exchange the grayscales for the display. And that can be done pretty fast and in real time. And the applications are, for example, changing the brightness. And as you can see here in the transform curve, if we change the brightness, we do not alter the slope of the transform curve. The slope still is 1, but we shift the curve to the left or to the right, which means increasing or decreasing the brightness. And if we are changing the slope of these curves, we change the contrast. And it's important to understand that although this image might look better to us in terms of the contrast as compared to the original, it is not carrying more information. No, instead of it's carrying less information. Because here in this part where we see the skin on the skull in this magnetic resonance image, grayscales are mapped together, which has been different grayscales in this image here. And that is also a problem if you're cooperating with physicians. They might come up with these images which are already altered. They think they are better, but for us as computer scientists, they are not, because we can nicely differ between grayscale 200 and grayscale 201, while the human cannot. And if you change the slope, you might change the inversion here. These are some examples. So what you can do with these histogram transforms. One example here is the stretching. If we have an image which is lousy illuminated, we could stretch that, and here are the examples. This is again a piece of bone structure where you might not see anything, and with this transform curve you end up with this image here, or for us showing a better contrast. The second thing is the convolution, which is not only looking to one particular pixel, but looking to neighborhood. This is how the convolution is defined mathematically, but I will not go too much in this math, as we also have physicians here. I go more in the result of applying such filters. So this is the original image, and we have some certain masks here. As we can see, the effect of this mask and the effect of that mask is sort of noise cancelling, but also blurring, of course. And this mask here is doing the opposite. The edges may appear sharper than here, but also the noise is enhanced. And what is, I think, important to differ these principles, just to look to the coefficients of this neighborhood. So it's clear that a larger neighborhood has a larger effect than a smaller neighborhood. If the coefficients are just positive, it's more or less something like an averaging. And the averaging yields a smoothing. If we have positive and negative coefficients, then we have what is the contrast enhancement. And here's some other kernels, again, enhancing the contrast. These kernels here are easier to calculate because you do not need to normalize. If you add on all the coefficients, the sum is 1. And here the sum is clearly not 1, and this is why we need to normalize and have it computational more expensive. And one particular filter is what is called a Sobel filter. These are particular masks where we have positive and negative coefficients. Now we have this smoothing sequence 1 to 1, which was here again, 1 to 1, 1 to 1, and if you fold that, you end up with these things here, and that is 1, 4, 6, 4, 1. And if you remember maybe your mathematics class, we have this Pascal triangle where you start with a 1, and then you compose the sum, so 1, 1, and then 1, 2, 1, and then it's 1, 3, 3, 1, 1, 4, 1, 4, 6, 4, 1, and so on and so forth. That is the binomial distribution as the digital representative of the Gaussian distribution. But again, we are back here, and we can see that these filter obviously detect some edges, and the direction of the edges depends on the orientation of the filter. And I can create something like an edge image using these coefficients. And edges, we already have learned, is an important thing to describe an image or a part of the image. In this case here, maybe the dental implant. And then we have the example of a Fourier transform, but the Fourier transform is not the only example of this transform paradigm, where sometimes you do the transformation in order to do the processing in a different space and have the inverse transformation, which still is less expensive, computationally expensive than going the way directly. And I think the example you all know is a logarithm. Logarithm is transforming the multiplication to an addition. And the Fourier transform is transforming the convolution into a multiplication. And that is the reason why we use these transforms. Here's one example, actually not from the medical field. What we see here is the sewer pipe, the internal structure of the sewer pipe. That is taken with a robot. The robot actually takes pictures every 5 centimeters, and from that you can compose a 3D view. This is a cylinder, cut it open and then flatten. So we see this is an area where usually the water goes in. And here is an inlet from another pipe, which has been lousy built. So we have these scratches here and so on. But that is not the reason I want or why I'm showing the picture. If you compare these two pictures, you will see due to the picture every 5 centimeters, we have these lines in the reconstruction. And in order to get rid of such lines, this regular pattern, we need, it's not working with a small neighborhood. We need to consider the entire information from the image, which is this one here. Sort of magically, it's almost the same. You will not find differences also here in the details, but these lines have been removed. And that is, for instance, what could be done with the Fourier transform. We go in the Fourier space, we black out the particular frequencies, and then we transform back. But this is just an example. So that were tools for image enhancement, and now we will go for tools for feature extraction. We have texture properties which result in texture features, and shape properties which result in shape features. So what is texture at all? Well, we have concepts like coarseness, regularity, orientation. Remember the Brodach's textures I was showing you. And the question or the problem is that there is no unique description of these things. You can define a lot of mathematical representations, or trying to find mathematical representations that allow you to differ between the different textures. So the solutions we have are maybe statistically, they may be from the signal theory or from the fractal. In the one case, we assume that the texture is due to some random process, and we use tools to cope with random processes. Here we are assuming the texture being more regular, and regular structures can be described with the Fourier analysis, for instance. And I give you some examples here. The concurrence matrix, the Fourier analysis we have talked already about, and the box count. And you will see that, again, this type of processing can be represented sort of with the neighborhood data generating the feature value. The next I think are shape properties. We have the description, for instance, which are area related, such as the compactness, which simply says, well, 4 pi times the area divided by the perimeter squared. I get something that describes the perfect circle with the number 1. And if the border becomes more irregular, the value here becomes lower. And we have curvature-related things. I will give an example here from the curvature scale space describing the curvature. and curvature properties of the borderline of an object. And again, we will see that this one here, of course, can be calculated in the neighborhood where the segment is placed. And we will see that, for instance, the curvature scale space also is composed of filtering of the data. And Fourier descriptors, I will not explain anymore, but we already talked about the Fourier as a mapping from the entire image. And if we have an object, of course, then it is sufficient to map the part where the object is located. What is the curvature scale space? These movies are not running, unfortunately. Okay, but I have this slide here with the end of the process. So what you are doing, we see the fish here. And the white points are the inflection points. That means where the curvature change from positive to negative. And we smooth the curve iteratively until all the inflection points have vanished. That is the result here. All the inflection points have vanished. And that figure here would track the position of these points. And as you can see here, that ends up with a certain pattern describing the shape and the properties of this certain pattern, and that's the reason why this curvature scale space is used in the image processing, is that is invariant to shifts. If I shift my figure in the image, that pattern looks identical. What happens if I rotate? Well, if I rotate, then the starting point may be shifted, which yields in the shift of the x-axis here. Sorry about that. It should be read x-axis. And the translation, well, may shift that in. No. That should be, the shift is the translation. It was invariant with the translation, and that should be the scale. So we have RST in rotation, scale, and translation. That should be scale. But anyway, what you see here, the step was the smoothing with the Gaussian kernel, which again is a sort of region-to-point mapping. Now we come to the deep learning. What is deep learning? We discussed that yesterday. We have artificial intelligence, machine learning, neural networks, and deep learning as a particular part of these neural networks. And what I was not talking about yesterday, but we will briefly analyze today, is deep learning, neural networks, multiple layers, backpropagation. That was the stuff from yesterday. But what we have not addressed is what is called convolutional neural network. And you have learned that the convolution obviously is a very central part in all this image processing. It is used for image enhancement. It is used for feature extraction, both for textures as well as borderline features. And this is also what we have in this mappings here. So for all these things, we use a convolution. And now the idea of these convolutional neural networks, the idea is why do we put a lot of efforts in manually engineering features, in manually designing filters, and so on? Why not give the task to the network? And the solution for that is what is called the convolutional neural network. And here is one example of the architecture. And what you can see here is the convolutional layer. That means we do not have fully connected layers, but we connect the layers in sort of that they are doing the filter. And the filter coefficients, well, they correspond to the weights associated to these lines. And so in the convolutional layer, we just have, for instance, if the mask is 3 by 3, we just have 9 different weights, although the interconnection here is for each pixel in the resulting image with a neighborhood corresponding to the source image. And that has 2 advantages. The one advantage is that we have immense reduction of parameters, which makes it easier for training, and we need less data for that. And the features are learned and not engineered. And this is a typical structure of a neural network. So we have the feature learning, say that way, due to all these convolutional layers. And again, you also see that we have this network architecture where the layers here become smaller than the input layer in terms of number of nodes. And then we usually flatten that into our feature vector and do the classification with, again, neural network layers. And of course, there are many different architectures published which are doing the convolutional operation. One very good performing example might be the UNet. And so I choose just that network in order to show how it works. Again, we have these convolutional layers here, 3.3, where a set of filters actually is designed, a set of coefficients. Transforming from the one here to the other is not only designing one 3 by 3 mask, but designing several 3 by 3 masks. And we do that over and over. Here we only have a few neurons, a few thousands, 1,000 neurons left. And then we decrease the resolution. We have these loops here, which are considered as memory. Remember the recurrent unit neural networks, and that results in the unit which is combining actually convolutional neural networks and recurrent neural networks. And that works pretty good, for instance, for segmentation. And if we want to visualize what the network actually is learning, now we can look to these layers here. And this is one example of these different layers where it is visualized how the filter coefficients which are determined by the network look like. And here this looks clearly like corner detectors, but if you go more in the detailed level, in the deeper levels, it becomes a little bit weird, what features actually are extracted. But this is what the neural network is resulting. Okay. Keeping that in mind, I will just give you one example. And the example is not really from human medicine. It's more from animal medicine. And the example is here from horses. I will explain what horse hoof trimming means, how it is documented. If veterinarians or hoof orthopedists are doing that. We will see how we can use artificial intelligence in order to optimize the localization of hoofs in images and also for defining the view. We will go for one example where all these algorithms are integrated in a smartphone app, doing the automatic cropping of images, and I will also go for AI using to measure the hoof conformation automatically and the future perspective. But what you can see here, we have a horse hoof that is front left, front right, back left, back right hoof, and we have different perspectives. The one is frontal, as the name would say it, and captured in front. Dorsal is that direction here. Lateral is from the side. Medial is from the inner side. And of course, it's hard to distinguish these images here from that one. If you flip it, you will not see the left leg from the outside or the right leg from the inside. That looks pretty similar. But we have this one here from the ground and from the back. And as you can see, these images here are pretty unstandardized. It's time-consuming to take these photographs. It's a lot of photographs, 4 hooves, 6 views, and 2 times before and after the trimming. And the task the human needs to do is not only the imaging. It needs to transfer these images. You need to sort the images. You need to label the images that they are on the right position here. So composing something like this manually takes a lot of time. However, you need that for the report. And so what can we do with artificial intelligence here? So the first thing is, what about automatic localization of the hoof and also determine the direction? And we had a data set of about 2,500 images now from 6 horses where ground truth was labeled. So for the hoof, we have the location and the view. We have a second data set composed from the internet, where we simply seek for horse hoof, or the German word Pferdehoof, and get these images. And these images, of course, have not been labeled, but they show horses or hoofs of horses. And we did that, and I will show in the result that is meaningful. Keep in mind what we have learned yesterday. Try to get the broad view and not to focus too much on your real problem. And if we combine that, we end up with something like 4,000 images. And here are some examples. These are the images which have been delivered and labeled from the hoof orthopedist. And here are some images from the internet, also showing hoofs, but in very different views. And also in very different scales. Here the entire horses, here just the horse hoofs, and so on. So then the next question was which network architecture to use. That is what you usually need to decide when you design these things. We were looking for neural networks that are able to run on low computational resources like a mobile phone, a mobile device, but also still able to, be in real time operated. And there are some of these standard networks. I will not go too much in the details here. These are 3 things taken from the toolkit. You have the libraries, and you usually do not go into the layers. You seek for a network that might solve your problem best. And if you're not sure, you compare these problems. Hopefully doing with all these steps Tim yesterday addressed. For the evaluation, we defined the average precision, average recall, and then the network architectures here. We can see basically the efficient DET network. The input, we have the network here, which is decomposed into two parts. Not go too much in the details here, but what you see here is one thing which is called the box head and the class head. So here we do the localization, and with the same output, we do the view detection. And that we do for all the three network architectures. Yeah, this is just one representation here of this particular network. I will not go in the details of the other networks, how they are composed, but to the results. Yeah, and what you see here is if we just train with the hoof orthopedist images, and if we train with a full data set. And if we train with a full data set and then apply to the hoof orthopedists, we end up with better measures as if we just train with the classified images. Yeah, so take an additional image, although not having the ground truth for that image, in terms of the view, results in better performance of the network. Yeah, and here are some examples from the localization. That are the images, and you see the boxes here with a percentage between 0 and 100%, indicating how good the network thinks this is for sure a hoof. And in our processing, we are taking that one not necessarily with the highest confidence, but we take this the region for the automatic hoof localization with the more centered one, as we suppose that the photograph tries to capture the hoof. That is a heat map in terms of the idea to visualize what information or where the information the network is using to decide is located in the image. And as we can see here, the hotspots are actually on the places where the hoofs are. Unfortunately, this is different images, but anyway. We can see the hoof here, we can see the hoof here, and these are the hotspots. Remember the wolf we had yesterday, where the hotspots were outside the face of the wolf. Here, that indicates that the network is doing meaningful things. And regarding the view detection, we are not able to differ 6 views. So the performance here is not really good. That is what I explained. If you look to that side here, or if you look to that side there, you will not differ that. So if we map lateral and medial, we also end up with quite good classification of what type of hoof it is. And so we integrated that all in a smartphone app. That means you take the picture, the network runs more or less in real time. You not notice the delay, which is a few milliseconds. To localize the hoof, we increase the height, as we do not want only this area here, which is detected by the network, but this one here, we add and we crop automatically, and we performed evaluation study with additional 7,500 images from hoof orthopedists, which have not been labeled, but which has been taken in this particular directions, and we generated a tool in order to provide the ground truth, and these are the results here for the classification, which is really good working. So that all integrated in the app then yields in something like this one here. This was what I showed you before, and these images, when captured by the hoof orthopedists, were automatically transformed in something like this. You do not need to sort the images, you do not need to crop the images, you do not need to put them on the right place here. That all can be done automatically. But that is not the only reason why these stock photographs are obtained. What the physicians are doing actually is doing measurements on the hoofs. So what is called the hoof conformation. And for that, the bounding box is insufficient. We need a network that gets actually the region. That is shown here. From that, we calculate the borderline. In that case, we are not interested in the internal structure that had already been used for identifying the object. So we get the outline. We find the corner points in the outline. From that, we calculate the segments. And then we calculate straight lines approaching these, or best fitting these outlines. And that gives us the relevant points in order to do the measurement. Unfortunately, I forget to put the image in the presentation where these measures actually are defined. But what we have here, we have a certain length and we have certain angles. You see, these are the angle measurements and these are the length measurements. And that all is in this application here, which is already available in the Google Play Store. So if you have horses, you are invited to download that and play around with it. No sound here. But this is a little bit about the future. We didn't check the sound. Oops.
Extremely futuristic idea at its time, and it still is. But in many ways, we are inching closer to making it a reality. A working tricoder could bring on a new era in medicine. Instead of expensive machines and long waiting, the tricoder is the ultimate digital health tool. It's a scanner, an analyzer, basically a Swiss Army knife for physicians. It was an extremely futuristic idea at its time, and it still is. But in many ways, we are inching closer.
I'm sure you all are recalling that device from Star Trek, where the doc is just going over the patient and getting the diagnosis. As we can see in this picture here, a vision from 1966, my birth year.
It could make the biggest promise of digital health real.
And I will short abbreviate these images. You will find a lot of those in the internet. The reason for me showing that is the idea that we have the technology really available after the 60 years. And what we want to do as the next step in this horse hoof project is also to automate the imaging process completely. So far, still you need to capture in the 6 views, which is computer assisted. But what about using structure for motion in order for 3D reconstruction, where you just have your mobile phone going around the hoof in any direction? And these are the first results we obtained here. Not perfect yet, but very promising, at least from my point of view. So I got the sign to conclude, and I will do. Pretty 2 minutes left. So the summary. We had the different steps of medical image analysis, which we all can more or less represent with something we call the convolution, a mathematical operation. That holds for image enhancement as well as feature extraction. And we can build convolutional neural networks that are exactly doing the thing, and to determine the parameters. Keep in mind the edge crisping, where we have -1, 5, and all these numbers, which are in that case done manually, are now done by the network. And that is why these convolutional neural network are that good performing for image processing tasks. And of course, they are also performing for signal processing tasks, where you not have a two-dimensional convolution, but a one-dimensional convolution. The principle is the same. And now the last slide with the last 3 take-home messages. So all steps, the medical image analysis can be reduced to the mathematical operation called convolution. Convolution parameters are the kernel signs and the coefficients. That is what I need to put in the design of the network. And both could be configured also automatically if I use, for instance, unit architecture that combines convolutional neural network with recurrent neural networks. What do you see here? It's a similar picture as we started. No, not a face. No, actually, it's a dog. Here, the Dalmatina. Yeah, this is the face of the dog. Here are the legs. This is the body. And once you have seen the dog in that picture, you will always recognize the picture. And although we have this nice lecture with all these convolutional neural networks, even the convolutional neural network is not still able to end up with Dalmatina or dog from that image. And that ends me. I think I'm perfect in time. Thank you very much for your attention.
Thank you so much, Dr. Thomas Deserno. We will be back at 9:45 with a lecture in bioinformatics and anomaly detection. So stay tuned and thank you for your patience. Thank you, everyone.